Okay, I want to spend a little bit of time, just a quick video here, looking at series and parallel combinations. So here's the bottom line. Okay, this is really, once you know the rule, it's very easy to apply the rule. For series, the same current must flow through all elements. So we have one resistor, another resistor, another resistor, and there's nothing being tapped off anywhere. So the current that goes through here must also go through there, must also go through there. Same current, all three elements, those are in series. But if there's anything being tapped off anywhere, so for example, if this goes off and there's some other resistor over here that goes somewhere, then that's not series, because the same resistor, or the same current that goes through here, some will go through here, some will go through there. So that's definitely not a series connection. However, whatever current that goes through here does go through there, so those two are connected in series, but not all three. So that's the rule for series. All the current, or the same current, must flow through all the elements in order for them to be in series. So all you have to do is look to see, are there any other paths for current to take? If there are, then you can say that they are not in series. For parallel, it's the kind of the reverse rule. For them to be in parallel, we must have the same voltage across all of the elements. So in this case, imagine that we are thinking about the voltage here. There's a voltage. That is because this is just a wire and this is just a wire. We have the same voltage from here to here as we do from here to here, as we do from here to here. Those three resistors are in parallel with each other. So very easy. If the same current flows through all the resistors, or any element for that matter, then they are in series. If the same voltage is across all the elements, then they are in parallel. Very simple rule. Let's look at an example. Suppose I have something that looks like this. And are these two, let's say R1 and R2 and R3. Are R1 and R2 in series? Well, we start from here, we go down. Current splits. No, R1 and R2 are not in series. In fact, R1 and R3 are not in series. R2 and R3 are not in series. None of these resistors are in series combination. How about parallel? Any of them in parallel? Well, let's see. Clearly, if we applied a voltage here and here across there, let's say V is applied there, we don't have the same voltage across R1 and R2. Don't have the same voltage across R1 and R3, so they're not in parallel. So this is a scenario where they're neither in series nor in parallel. In fact, this is what's called a Y connection, and we will see that that's related to something called a delta connection. How about this? There's R1, R2, R3. Are those in series or parallel? No, those are not in series, nor are they in parallel. First of all, we don't have just two terminals to grab, right? So if we grab here and here, and we want to know what's the equivalent resistance between those two terminals, here's what we would do. If there is no connection at that point, then we know that the current through here must also go through there. So then R1 and R2 are in series. So if that is the case, then we can replace R1 and R2 by a single resistor. See if I can make that eraser a little bit bigger here so that I can get rid of some of this stuff quicker. So we can now replace let's call this equivalent, which is equal to R1 plus R2. Now from this point to this point, what's our equivalent resistance? Well, if I apply a voltage here, or measure a voltage, the same voltage is across R3 as it is across R equivalent. So R equivalent and R3 are in parallel, and so the whole thing could be replaced by R3 in parallel with the R equivalent. So our total equivalent resistance in this case would be R3 in parallel with R1 plus R2. Alright, I'm going to stop there. This is just intended to be a quick illustration, but remember, the key is same current, then in series. Same voltage, then in parallel.